Ghosh, am I audible? You can type a message if you have any problem with the mic. Thank you. So anyway, it is already 6:05. So we'll start. So meanwhile, the others will join. So as I mentioned in the last session, today we will again discuss the losses in pipes. So in this session, we will start with type of losses like major losses and minor losses, and we will see the formulas for computing this loss of energy, and followed by three previous year gate questions we'll solve. Okay, so let's get started. So I'll first share my screen. Okay. Let me go to the full screen mode. Go shop. If please let me know if if my slides are not visible. Okay. Okay. So this is a session number 10. So this is session number 10. Yes. So let's start with the losses in pipes. Okay. Suppose imagine there are two reservoirs, reservoir A and reservoir B. Okay. If the flow is taking place from reservoir A to reservoir B, okay, in this manner through a circular pipe. Let's say imagine there is a circular pipe. Okay. So at this particular location, if we insert a piezometer, the head available with the water will be shown as this much only. Okay. So after the flow enter into the pipe, if you insert a piezometer just next to it, very minimal, then you will observe there is a declination in the total available head, and this particular loss is attributed as entry loss, which is denoted as 0.5 v square by 2g. Okay, which can be computed as 0.5 v square by 2g. Similarly, as the flow moving to the reservoir B, the flow encounter a loss due to the friction. Okay, and if you draw the line, energy gradient line. Okay, if you draw the energy gradient line, you will observe this kind of phenomena. Okay, the declination in the available head. So and after that when the flow exit from this pipe at this particular location also, we will experience one loss termed as exit loss. Okay, that will also be considered. So which is v square by 2g. Okay, this is a general case. So when the flow taking place from reservoir A to reservoir B, it encounters multiple losses. In this case, particularly, it encountered an entry loss and loss due to friction and exit loss. Okay. Suppose and this entry loss and exit loss are termed as a minor losses. Why, how with this minor and major divided? Because based on the amount of loss. Suppose if we computed the energy loss due to the friction, which is much higher than the energy due to the entry loss and exit loss. So because there is a difference in the quantity, so that's why it is divided as a minor loss and major loss. Okay, so on the right side of the slide it is I have written major loss, which is loss due to the friction. This will be computed by using Darcy's formula, Darcy-Weisbach formula, Weisbach equation or formula. So which is HF equal to FLV square by 2ZD. So here I think all of you know the terms individually. Maybe I can explain one more time. F is the coefficient of friction, L is the length of the pipe, V is the velocity of water in the pipe, and G is acceleration due to gravity, D is the dia of the pipe. Okay, dia of the pipe. Suppose let's say imagine the pipe is circular. Let's say imagine the pipe is circular. Then for the circular pipe, the area can be computed as pi by 4 d square, or if we have this radius, then pi r square. Okay, and as we know, the discharge formula is equal to Q equal to AB. Here A is the area and V is the velocity. Let's say if I want to replace V in this place, in Darcy's Weisbach equation with Q, then we can do the following procedure: V equal to Q by A. So A we know from this the equation, which is 5 by 4 d square, then 4q by 4 d square. So I think you know how you got. Maybe I can derive one more time. 5 by 4 d square. Suppose like under this 4 will go up, so 4q by pi d square. Okay. Suppose then substitute in this particular equation, and let's say if we assume g is 9.81, then this final equation comes as FLQ square by 12.1 into d power 5. This is also one important formula we can remember, because most of the cases our interest is to compute the discharge rather than the velocity. So it would be beneficial for us to know the formula in terms of the discharge. Okay, so the formula, this is one important formula and this is another important formula. Okay, so this is related to the major loss. Let's move to the minor losses. As I've shown you earlier, there is a multiple losses. First, if we see, there's a loss of energy due to the standard enlargement. So how it looks like? Let's say this is a smaller diameter pipe. Suddenly, if we put a bigger diameter pipe, okay, until this point, the water is coming with a higher velocity v1, and as soon as this diameter is increased, the flow experience a decrease in the velocity, which from v1 to the v2. Suppose if we compute the difference in terms of the head, it will come as v1 square by v2 square by 2g, which is loss of energy due to the enlargement. Okay, and similarly, a loss of energy due to the sudden contraction and entrance. So what is a sudden contraction? Suppose let's say this is a bigger diameter pipe and this is a smaller diameter pipe. So from this to this, if the flow is taking place, so here there will be a loss of energy, which become computed as k into v square by 2g. So here the k is a loss coefficient. So which will be given in the question. Otherwise, it is 0.5 of v square by 2g. Okay, and loss of energy at the exit of the pipe. At the exit of pipe. Okay, at this particular location, we experience, if we computed the total energy, that will be a sudden drop, which is equal to the v square by 2g. Okay, and similarly, loss of energy in the bends, which is equal HL, which is equal to k into v square by 2g. Similarly, loss of energy in various pipe fitting. See here, the k represents the loss coefficient, which is varies from the loss to loss. Suppose in this case, sudden contraction entrance, this is a 0.5. For exit pipe, it will be 1. So if I want to put k, then I can keep as k as 1. So for energy in bends, we have some loss coefficient. Similarly, various pipe fitting will have some different coefficient. So for each type of phenomena, we have a different kind of loss coefficient. Okay, so the main important formulas are this formula and this: loss of energy due to sudden contraction and entrance, as well as the exit of the pipe. Okay, If you can able to remember this formula, then it is sufficient. So for entry, for a contraction and entrance, which is equal HL equal to 0.5 v square by 2z, whereas at exit of the pipe it is v square by 2z. Okay. So so far what we have seen major loss as well as minor losses. So what is a major loss? Loss due to friction, HF, and under the minor losses, exit, entry, next to enlargement, contraction, bend, gate valve. See, all these things will result into a loss of head when the flow is taking place from one higher gradient to the lower gradient, like from a higher gradient to the lower gradient along the gradient. Okay, so let's move to the question. So what we do, we'll solve one question, three questions in this particular session. So now let's see the first question. This question is from GATE 2014 set 1. The question number is 47. So the question is as follows: an incompressible fluid is flowing at a steady rate in a horizontal pipe. Okay, this is a condition. Suppose from a section the pipe divides into two horizontal parallel pipes of diameter d1 and d2. Okay, so and where d1 equal to 4d2. So here they have given a relation between the two pipes, which is equal to d1 equal to d4 d2, and that run for a distance of L each. Here the distance for the of the both pipes is same, and again join back to the pipe of original size. Okay, from for the both parallel pipes, assume the head loss due to friction only, and Darcy-Weisbach friction factor to be the same, and compute the velocity ratio between the bigger and the smaller branched pipes. So here, what is a bigger pipe? That is pipe 1, and the smaller one is pipe 2. So the question is to compute V1 by V2. Okay. So I'm giving just 1 minute time. Just think and give me idea if you have anything. How we can solve this question. Ghosh and Nikesh Sharma, you both can try. No, sorry, the slides are not visible here. Can you guess how we can solve? So the question is as follows: like there is a pipe. Suddenly, so what they did is they divided this pipe into two sub pipes. Again, they joined back the pipe. Okay, let's say if this is a one pipe, this is second pipe, this is D2 and this is D1. They mentioned a D1 equal to 4D2, like that. Now their interest is to compute the V1 by V2. Okay, so as we know, as I discussed in the previous session, first case 1, when two pipes are connected in parallel, the discharge in both the pipes will be same. And the second point is that, sorry, the discharge could is equal to total discharge equal to Q1 plus Q2, and the loss of head, total loss of head HF1 is equal to HF2. These are the two conditions we use when the two pipes are connected in parallel. So similarly, if I ask, then what is the what could be the conditions for series? So this will be Q1 equal to Q2 and so on Qn, but the total loss of head will be equal to HF equal to HF1 plus HF2 plus HF3 and so on. So these are the two conditions to be remembered. So when the two pipes are connected in parallel, it follows the continuity equation that Q equal to Q1 plus Q2, and the total loss of head in both the pipes, HF1 is equal to HF2. Okay, so we use these two conditions to solve this question. So this is a 2 marks question, but it hardly requires one step to get this V1 by V2 answer. So just see what I have done here. Suppose this is a schematic diagram of the question. So this is one pipe for initial pipe and is divided into two branches. So this is one first pipe, this is a second pipe. Okay, and where d1 equal to 4d2, there is 5, we have velocity of v1 and q discharge of q1, similarly v2 and discharge of q2, and in the question it is mentioned that hf1 f1 and f1 and f2 are both equal. So friction factor, the Darcy-Weisbach friction factor to be the same, as well as the distance of the both pipe is also same, which is L. So L equal to L1 plus L2, and as well as friction factor also F1 and F2 equal to F only. So as I mentioned in the previous slide, when the both the pipes are connected in parallel, the head loss is same. So let's say with this assumption, we will equate the HF1 equal to HF2. HF1 is nothing but the Darcy-Weisbach equation, which is loss due to the friction, which is equal to F1 L1 V1 square divided by 2GD1 equal to F2 L2 V square by 2GD2. Okay. Now what we know? We know that F1 and F2 are equal, L1 and L2 are equal, and D1 have a relation with D2, and G is also equal at the both the cases, and 2 is also equal. Let's see if what I can do, I can cancel straight away. Here also I can cancel because F1 and F2 equal to F1 and L1 and L2 equal to L2. So what we left out? We left out with V1 square by D1, V2 square by D2. As we know, D1 equal to 4D2. So if I substitute V1 square by 4D2 and V2 square by D2, and D2 also can cancel. So it will be V1 square by V2 square, which is equal to 4. So if one want a ratio of V1 by V2, what we can do? We can simply do the square root of it. So we can get V1 by V2 equal to 2. This is simple, very simple question, but it carried 2 marks. Okay. So the only trick is that to know that when the pipes are connected in parallel, the head loss is same. If you know this particular trick, then this is straightforward question. Okay. Is it clear?
Yes, sir.
Okay, let's move to the next question. Okay, let's see what this question. This question I have taken from GATE 2015 set 1. This is also 2 marks question. See, when the question comes from the losses pipes, this will be definitely a 2 marks question, and it is very straightforward only. It will be very straightforward and a formula substitute type of a question. Okay, let's see this question. So this question I have taken from GATE 2015 set 1, question number 53, which and this question is for 2 marks. Okay, the question is as follows. The two reservoirs connected through a 930 meter long and 0.3 meter diameter pipe. Okay, the pipe which is connected between the two reservoirs has a length of 930 meters as well as a diameter of 0.3 meters, and is also contained one gate valve. Okay, so now the pipe entrance is sharp. So remember, they mentioned that the pipe entrance is sharp and corresponding loss coefficient given as a 0.5. Okay, and the valve is half open. Due to this valve half open, there is a loss encountered by the flow, and thus loss coefficient is given as a 5.5. Okay, the head difference between the two reservoirs is observed to be 20 meters. Assume the friction factor for the pipe is 0.03 and G as 10 meter per second square. Now our interest is to compute the discharge after accounting all the minor and major losses in this particular system. Let's draw this diagram how it looks like. So they mentioned that there is a two reservoirs. She is connected to a pipe. Okay, let's say in this pipe reservoir we have this much water level, and in this reservoir we have water level at this location. If I look at the difference in height of water level at these two locations, it is given as 20 meter. Okay, this, let's see if this is the first reservoir and this is the second reservoir, and this pipe diameter how much they give, 0.3 meters, and the length how much they give, 930 meter length. Okay, and the friction factor how much they give, 0.03, and the G as 10 meter per second square. Okay, 10 meter per second square. Now can you tell me what type of there is a gate valve also here, so can you just briefly mention what type of losses we can observe when the flow is taking place from reservoir 1 to reservoir 2? You can volunteer here.
So entrance loss,
Entry loss, correct, entry loss,
then friction,
then friction loss.
and then the bulb. At the bulb there will be one loss.
Wait, and at the gate wall we have loss due to
Bulbs.
gate wall
Gate losses and
and
the exit loss.
correct, good, loss due to exit. Suppose let's say the total head difference between these two reservoirs observed to be 20 meters. Okay, now if this is the case, then why this 20 meter difference is observed? Because of these losses. Then if because of this, all sum of all these losses, so now what we can do is that if we sum all these losses what the flow is encountered, we will be able to we will be getting this 20 meter loss. So what is that? So it's nothing but, and the head difference is head difference between two reservoirs equal to sum of total losses. If there is no loss, you only tell me if there is no losses, there is no loss, then the total head and the reservoir 1 and reservoir 2 will be the same. Consider they both are located in the same height. Assume they both are located in the same height. Okay, so what will be 20 meter equal to entry loss plus friction loss plus gate valve loss plus exit loss. Okay, these are the total losses. Okay, suppose and do we know formulas for all these losses? Yes, we know. So I have shown you the previous slide. So loss of due to sorry, the loss of due to entrance is we know, loss of due to exit we know, and as various pipe fittings also we know, and pipe fitting gate walls also comes under pipe fitting only. Okay, now again let's write the formula. Okay, so this is a schematic diagram I have drawn in a more neatly. So this is a reservoir 1, this is reservoir 2, and the length of the pipe is 930 meters, and the difference in the reservoir levels is 20 meter, and the F is 0.03, and diameter of the pipe is 0.3 meters. So Can you tell me what is the formula for loss due to entrance entry?
0.5 b square by 2g.
V square by 2c. Even we know this zero point 0.5. Additionally, in the question they have given loss coefficient as zero point 0.5 also. Okay, that also you can observe. And loss due to friction,
So FL b square by 2zd.
correct. Good. FLV square by 2GD. And loss due to gate wall,
5.5 b square by 2g.
correct. 5.5 V square by 2G. And the loss due to exit,
B square by 2g.
correct. V square by 2G. Now let's sum all these things, all these losses and equate to the total head loss. So total head loss is 20 meter, and these are the total head losses we encountered, and the flow is taking place from reservoir 1 to the reservoir 2. So what we can do is that, since in all the terms this 2G is 2G is common, so we can take this one. Yeah, one hint like hint or suggestion I want to give is that, remember 2 into G value directly, which is 2 into 9.81, which is how much? 9.19 point, how much? 62. Okay, this value you always remember, because why I am saying is that, since all of you are using this virtual calculator, not the scientific calculator, so if in this case it would be difficult for you to enter all using keyboard to enter all these type of things. So it always remember some things can be remembered. Suppose if it said so, otherwise always consider G as 9.81 only. In some questions they will say that G is 10, then it is a very simple for you. But in the most of the cases, G given as a 9, G will be given as 9.1, and if they won't given also, you can assume 9.81 only. In that case, remember this 19.62 will be a good will be advantage for you. Okay. So now what we do is that, bring this 2G this side, to 20 meter into 2G is equal to K into V square plus FLV square by D, K, KGV square plus V square. So you can able to see how I got this particular equation from this equation. Now what we do is that, we know K is zero point 0.5, friction factor we know, which is given as 0.031, sorry 0.03, and L is given as 930 meters, and V we don't know, and D pipe diameter is given as 0.3 meters, as well as loss coefficient due to the great wall given as 5.5 V square, 5.5, and V square by 2G we know that 2G go on the other side, so V square left out plus V square. Now what is the common here? V square is a common. So what we do, we'll bring the V square out and we'll just sum all the remaining numerical value. So after doing that, so we get a value of V square equal to 4. So by doing the square root on both the sides, we can get V as a 2 meter. But that is not our interest. Our interest is to compute the discharge, which is equal to Q into AV. Okay. So, as we know, since it is a circular pipe, so the area of the circular pipe, pi d square by 4, and velocity also we know, which is equal to pi by 4 into 0.3 square into 2. The value is equal to 0.1141 meter cube per second. So the range is given as 0.14 to 0.142. This is a range given in the gate solution. Okay. So is it clear? Is it clear, or did I make you more confused? Like, did I confused you? Yes, sir, there. Nikesh or Ghosh, is it clear? Yeah, thank you. Thank you, thank you. So let's move to the next question. Similar question only, similar type of question, but slightly, sorry, what happened? Okay. Hmm. Sorry for the glitch. Okay. So let's move to the another question. This is also from GATE to 2015. You can see how frequent these questions are. This question actually is very important to me because I appeared. I wrote the GATE 2015 very first time. So for my MTech admission. So and and I attended for session two. So this is this was very surprising to me that time. So let's solve this question. What it is about. Okay, this question is from GATE 2015 set 2. The question number is 56. Okay, the question is as follows: a pipe of zero point 0.7 meter diameter has a length 6 meter and connects two reservoirs A and B. Okay, the water level in the reservoir is at an elevation of 30 meter above water level in the reservoir at B. Okay, let me draw parallel to this. Let's say this is A and another is a reservoir at B. Maybe this is like this and this is also like this. If I draw and the water level difference is this much. Let's say it is mentioned that a pipe is connected which is of 6 kilometer length and diameter is how much? 0.7 meter. Okay. So what is next? Off along the pipeline, maybe let's say at 3 kilometer, there is a branch through which the water is supplied to the third reservoir C. Let's say after 3 kilometer, what they did is that they connected one more branch and supplied water to the reservoir C. Okay. The friction factor of the pipe is 0.024. Okay. So this friction factor is applicable to all the all the pipes, and the quantity of water discharged into the reservoir C is, so how much water is discharging into the sea, which is equal to 0.5 meter cube per second. Considering the acceleration due to gravity as 9.81 meter per second square and neglecting the minor losses, which is what are the minor losses? Entry loss, exit loss, all these losses as well as gateway loss, all these neglecting all the minor losses. The discharge in meter cube per second into the reservoir B is dash. So our interest is to compute the QB. This is the QA and this is QB. So as we know, like let's say QA is entering into the pipe at this particular location, then Q how much? Then if we use this mass balance equation, it should satisfy this particular equation. Okay, nothing but the amount of water which is relating to QB will be equal to QA minus QC. Okay, this will be the condition. As we know, this is a QC is how much? 1.5 meter cube per second, and we don't know the QA and we don't know the QB. Now what we need to do is that we need to compare the QB. What is a QB? How much is a QB? Okay, this is the case. So can you guess how we can solve this question? And here the good part is that we know the head difference. So any idea how we can solve this question? So this is also same. So this is reservoir A, reservoir B, and the difference between the two reservoirs is 30 kilometer. and at midway at 3 km, the water is supplied to the reservoir C of amount of 0.15 meter cube per second. Okay, and now as I mentioned that total head difference is equal to loss up to the first of, let's say up from here to here there is some loss, plus loss in second half of the pipe. Let's say from here to here there is another loss. Now if we can able to compute these losses neglecting, here the question, in the question it is mentioned that neglecting minor losses. Okay, neglect the minor losses. So neglect the minor losses. By neglecting the minor loss, if we can able to compute this particular loss in first half as well as the second half, then we can able to compute the QB. So as in the very first slide I mentioned that it would be advantageous for us if we know that Darcy's Weisbach equation in terms of Q. So how we derived HF equal to FLV square by 2GD, considering pipe as a circular, and we calculated pipe area as pi by 4d square, and V equal to Q by A, which is equal to 4Q by 5d square, and we substituted this particular relation into this equation. Then we reached to the, then we got FLQ square by 12.1 d power 5. So I told you it would be advantageous for if you remember. Even though if you don't remember also we can still can able to do, but it will be little hectic for us in a gate exam. So but anyway I have explained earlier, so that is equal, that you can remember now. So HF, so loss up to the first of how much, because till this particular point from here to here the amount, the discharge value will be QA, and after this the discharge at this particular location will be equal to QA minus QC. Okay, this will be equal to QA minus QC only, no? Is it correct? Like, are you able to follow?
Yes, yes, correct.
Yeah, otherwise one way how what we can write, either this can be QB or this can be QB plus QC. Both are exchangeable. Okay, so now what we do is that we will write this head difference in terms of QB only, because our interest is to compute a QB. So now what we do, we replace QA equal to QB plus QC. Okay, so by substituting all the values, 30 meter equal to FA is given as 0.024, LA is 3000 meters, because it is given in the terms of kilometer. So 1 kilometer equal to 1000 meters. Okay, so 3000 meters into, so this is QA. As I have shown you, QA equal to QB plus QC. So I replaced QA with QB plus QC. How much is QC? They had mentioned that the quantity of water discharged into the reservoir C is 0.15 meter cube per second. So that is 0.15 plus FB also given as 0.024, and LB is 3000 meter, and QB is unknown. So we'll calculate the QB square divided by 12.1 into, what is the DA? DA is given as 0.7 meter. So it is zero point 0.7 whole power 5. And again here also 0.7 whole power 5, because it is given as dA power 5. The formula is dA power 5 as well as dB power 5. See, it may be little confusing for you why they like, because they, in this particular question they mentioned that a pipe of 0.7 diameter connected to the of sorry a pipe of 0.7 meter diameter has a length of 6 kilometer. So indirectly they mentioned that the pipe has uniform diameter from between reservoir A and reservoir B. So it is okay if you assume in that way. So zero point 0.7 at the both locations. So here by solving this thing we can able to come up with this quadratic equation. Quad, Quadratic equation. Because why we arrived at quadratic equation? Because sorry, here also square is there. cube, because this is an our interest is to cube, our interest is to compute a cube, which is of which is has a root, as a square of power of 2. So okay, so we will by simplifying this particular equation, we'll get a this quadratic equation. As we know, the roots of quadratic equation can be computed as, we can compute the roots minus, can you guys say
plus rho b square minus 4ac by 2a.
plus or minus square root of b square minus 4ac divided by 2c. Okay,
2a.
2
So
2a or 2c.
2a. Yes, sir.
Hmm. So in this case, if you and we may get one negative value, one like one negative, one positive root as well as one negative root. So consider as a positive root because and the flow cannot be negative, so you can neglect this root and we'll get with a positive value which is 0.572 meter cube per second. This is our answer. Imagine this question I was asked in 2015, and this is a like I appeared I've written the gate 2015. So now it is, now you know the answer, and how you now you know how you can solve. Okay, so that is all from my side for today. Uh, if you have any question related to this loss of pipe, I'll be very happy to answer you. See, what we do is that we will do one more session on the losses in pipes only. Okay, because like when I looked at the previous year questions, I have seen many questions from losses in pipes. Still, we did not cover the siphon question also. In what is the height of the siphon we can keep to avoid the suction and all. So that problem we'll cover, and we'll solve some previous year questions related to that part of siphon also. And there are many other questions uh, for 2 marks. I'm saying I'm only concerning right now. I'm only talking about 2 marks. If you take any previous year question papers, you can able to get at least one question from these losses of pipes, in both this any of this item. So it is very important and very easy scoring section. So only few formulas are there. As I've shown, like only the main formula is that what, loss due to the friction, HF formula, which is equal to FLV square by 2G. Yes, next time I'll include a little hard question. Maybe see, uh, this question I have taken from the board, but maybe next class I'll take one question from the Modi and Seth, the tough question, and in that question we will talk more. Okay. So yeah, my gate rank was 2000, 2800 in 2015. So it was, I did a self preparation. I did not went for any coaching. So my rank was 2800, and I joined in Guwahati as MTech fellow in water resources section. Okay, so in the next session also we'll talk on the losses in pipes. Traditionally we'll start with the same, what is the major loss and minor loss. And this time in the next session I'll take one big tough problem from the Moody and Seth textbook, and we'll talk all these things, and we'll solve again two previous year gate questions. One is from 2011, another I'll see what question I can solve. Okay, and on the next session again we'll stick to the fluid mechanics only. I'll update the schedule in the website. Please visit the website regularly, and write to me if you have any questions also. I'm providing my mail ID here, so you can use that mail ID and write to me if you have any questions. I'm very much happy to help you. Okay, if you have any questions you can ask me. I'll stay here only.
So there is one problem from 2017.
Hmm.
A triangular pipe is there.
Okay.
So please include that question in next session.
Okay. 2017. Huh?
Yes, sir.
Okay. I'll note down that point. And any other suggestions? So 2017 I'll include, and 2011 one question is there. I'll include that question also. Okay. So in the next session also we'll talk about losses in pipes. And do you have any suggestions what I can cover in the next to next session? Any ideas, like any weak areas you wanted me to cover, like tough areas, I mean to say. I'm thinking we can go with this fluid mechanics only, but like you using energy equation, Bernoulli principle and all, and Venturi applications of Bernoulli equation, like Venturi meter and piezometer, all these type of questions I'm planning to solve in the subsequent, like in the next to next session. Is it fine? Like, or should I go to the hydrology or hydraulics? Yes, sir. Okay, kinematics and dynamics I'll cover. Okay. So it is 6:51. If you have any questions, you can ask. No, it need not be a technical question. You can even ask other related question also. That is fine. Other questions also I can able to answer. Thank you, Ghosh. Thanks for joining. Please do join for the next sessions also. We'll have good sessions, and we'll solve like most relevant and important questions for the for your grade preparation. See, I'll mainly focus on 2 marks questions, because this is where you can able to score good marks. See, for 1 marks questions is always tricky. Sometimes like it comes from the theory, sometimes you will sometimes kind of a derivation, and 2 marks questions are kind of a formula substituting kind of questions. And if you know the concept and you know the fundamental assumptions assumptions about that concept, then you can able to score 2 marks easily. Especially suppose if you attended, like whether you attended our previous sessions or not, I talked about critical flow and hydraulic jumper, and while explaining this concept I narrow it down to only 4 formulas. If you can able to remember those 4 formulas, it is tight, like it's 2 marks is in your pocket only. Just the main major concept is that channel width contraction as well as the rise in depth. If you know these two concepts, it is very easy to score. Additionally, you have one hydraulic jump concept also. Okay, like see, these are the very easy to scoring areas, especially water resource engineering is good for scoring. Kind of hydrology as well as the open channel flow and these losses in pipes. These are the easy areas. Dynamics and kinematics is kind of a tricky part, but still it is a solvable questions you can do. But what my suggestion is that focus on hydraulics, hydrology, as well as these losses in pipes in these areas. So you at least among these areas you can able to score 6 to 7 marks easily. Okay, thank you. If you don't have any questions, we can wind up the meeting. Thank you. Please do join for the next sessions also. Thank you.